This is the Westlake High School Chemistry 1 video covering atomic structure. So we've talked a little bit about the history and what the concept of what an atom is. Well, now we're going to really get into what really makes up the parts of the atom. You probably, through previous videos or previous exposure, know the three parts of the atom: proton, neutron, electron. Today we're really going to hit on the details of those three parts. But just to give you a little bit of scale of the things that we're talking about, like the scale of atoms, if you were to take a single atom and blow it up so that the entire atom was the size of a baseball stadium, your nucleus, that part in the very, very center that Rutherford discovered, that positively charged center piece, would be the size of a marble sitting dead center in the air in the middle of your baseball stadium. So imagine that, a giant baseball stadium. If you've never been to one, you've seen it on TV. They're huge. Well, if you were to blow an atom up to be that size, the nucleus is so small it would still only be a marble dead center in the middle of that stadium. And like I said earlier, you probably are somewhat familiar with the various parts of the atom: the proton, the neutron, and the electron. But we're going to cover it here just to make sure that we're all super clear on those three. So the symbol for a proton is going to be pretty simple. It's going to be a P. Neutron is going to be an N. And electron was going to be an E for us. And there's really two ways to describe all three of these, and we'll get to each one of these here in just a second. Protons were discovered originally by Rutherford, and those are going to be our positive charges. Neutrons, as their name might kind of give away, are a neutral charge, so they really don't have one. I'm just going to put in A or 0, because that tells you the charge is 0. It's not applicable. There is no charge for a neutron, whereas our electrons are going to be those negatively charged pieces. So we can use these relative charges to describe part of the symbol. So a proton isn't just P, it's a P with a little plus in the upper right-hand corner. A neutron isn't just N, it's N with a little 0 in the upper right-hand corner. An electron isn't an E, it's E with a negative in the upper right-hand corner. These are going to be the most common abbreviations that you're going to see. I'm going to go ahead and give you three more. Include them. You're going to understand them a little bit better here in just a second. So proton would be 1, 1. And notice I'm putting the numbers on the left side of my symbol here. Neutron would be 1, 0. And electron's going to be 0, negative 1. We'll talk about what all of those numbers are on the left side of my symbol here in just a second. But again, either one of these symbols are useful. Whether you're using the left ones or the right ones, you do need to understand that they mean effectively the same thing. So we've gone through our symbols, we've gone through a relative charge. Now let's talk about masses. Rutherford discovered that all of the mass of an atom is in the very, very, very center of your atom, in that nucleus. Well, through experimentation, we also discovered that the only two things that lived there were protons and neutrons. So we know that our protons live in the nucleus, and we know that our neutrons live in the nucleus, and the electrons are constantly floating around outside the nucleus. And sometimes we call that area the cloud, or the electron cloud. So we have protons and neutrons in the nucleus, electrons are floating around outside. According to Rutherford's experiment and discovery, we know for a fact that all of the mass of an atom is effectively held in that very dense nucleus, that very dense center. So, also thanks to Chadwick, we know that the nucleus and the neutron and the proton weighs about the same. So, just for simplicity's sake, we're going to say that the proton and the neutron have the same mass, they weigh the same, and they both weigh 1. They're kind of the basis of our scale. So 1 proton weighs the same as 1 neutron. Now when it comes to electrons, we proved that all of the mass of an atom is in that dead center nucleus. Well, electrons don't live in that dead center nucleus. They're flying around all around that nucleus. So we're going to say that electrons have no mass. Now that's really not true. They have a very, very, very small amount of mass. They are considered matter. The thing is, that mass of an electron is so small compared to the mass of a proton, it's effectively nothing. So for our simplicity's sake, we're just going to say protons and neutrons have a mass of 1, and electrons have a mass of 0. Okay, now it's time to talk about those numbers that I was adding to the symbols a little bit earlier. There's 2 numbers that are both very, very important when we start writing atoms and start writing elements, and that's the atomic number and the mass number. So let's talk about the atomic number first. The atomic number is abbreviated with the letter Z because science can never be straightforward, apparently. That atomic number is what defines that element as that element. It is equal to just the number of protons. Carbon is carbon because it has 6 protons, period. That's the end of the story. If you suddenly have something that doesn't have 6 protons, that element isn't carbon. It's nitrogen, or it's oxygen, or it's something different with a different number of protons. But the atomic number is the number that defines that element as an atom of that element. So it's just the number of the protons. The second number that's very, very important is the mass number, and the mass number is abbreviated with A, again, because what is science if not confusing at times? And the mass number is the total number of everything in your atom that has mass, which based on the chart that we just used is going to be your numbers of protons plus your number of neutrons added together. It is the total mass of an atom. Your mass number will always be a whole number. Okay, it is not the number on the bottom of the periodic table. That's something that we're going to talk about here in just a little bit. Okay, but our atomic number can be found on the periodic table. It's the number in the upper part of the box. The mass number cannot be. Okay, you're going to have to do a little bit of finagling to get the mass number. And we'll show you some examples of how we find the mass number here in just a little bit. We use these numbers in conjunction with our symbols in order to very quickly and very clearly tell scientists, here's what element this is, here's the mass of that element. Okay, so my mass number will always be on top. My atomic number will always be on bottom. Now notice, the top number should always be bigger than the bottom number. Okay, except in a couple very, very rare cases. Typically speaking with hydrogen. But 99% of the time, your top number will be bigger than your bottom number. Okay, so that's just a shorthand way of describing atoms and elements. Here's an example atom that we have here. You have a nucleus with 8 protons and 8 neutrons. I went ahead and told you that it's an oxygen atom. That's okay. And it shows a bunch of these clear electron energy levels. Note these distinct rings. That's what Bohr said an atom should look like. Well, our A is our mass number, the total number of everything that has mass. So in order to figure that out, we're going to have to look at the nucleus where all the mass is contained. Well, in that nucleus, I have 8 protons and I have 8 neutrons, which means my total amount of mass is going to be 16, 8 plus 8. Everything that has mass is included in the mass number. When I look at Z, the atomic number, I only want protons. So my Z is going to be 8. Okay, so total mass is 16. My Z, my atomic number, is 8. So if I want to kind of count individual particles, individual pieces of my atom, I have 8 protons, because it says so right there in that box. neutrons, well, I have 8 for again, the same reason, right there. And you can sit there and count all of your electrons. 1, 2, 3, 4, 5, 6, 7, 8 electrons. So, when I'm trying to write my symbol, when I'm describing in shorthand this atom, I'm going to have 16 over 8, right? Big over small. And I need the symbol for oxygen. You should be starting the process of learning element to symbol, symbol to element. Okay? We are going to have to memorize that. So, if you haven't memorized it yet, that's okay. Keep working on it. But also, if you look at your periodic table, you can say, okay, well, I know that my atomic number is 8 because I have 8 protons. I can look at the periodic table and find the little box that has the number 8 in the top. And oh, hey, it's oxygen. And it tells me that the symbol is O. So even if you don't know that oxygen is O yet, that's okay. You can still look at the periodic table and get the symbol. So notice earlier that I was really emphasizing this idea of the number of protons is what makes that element that element. It is the atomic number that defines the element as that element. Well, here's why. Because you can have multiple atoms that are the same element, but look a little differently. This is one of the pieces of Dalton's atomic theory that had to be corrected. Dalton originally said that all atoms of the same element are identical. In other words, if you have a carbon atom, it looks exactly like every other carbon atom in existence. We know that isn't true anymore, and it comes down to this idea of isotopes. Atoms of the same element that have different numbers of neutrons. So they're the same element because they have the same number of protons, but they have different numbers of neutrons, therefore they have different mass numbers. And that's why mass number and atomic number are both really, really important. The atomic number defines the atom as a particular element. The mass number gives it a little bit more of an identity. Here's one example of 3 of the same element that all have different isotopes. I have lithium-6, I have lithium-7, and I have lithium-8. They're all lithium because they all have 3 protons. That's what defines lithium as lithium. What makes them a little bit more unique is that mass number, the number of neutrons. Lithium-6 is going to have 3 neutrons, right? 6 minus 3. Lithium-7 is going to have 4 neutrons, 7 minus 3. Lithium-8 is going to have 5 neutrons, 8 minus 3. So different numbers of neutrons gives you different mass numbers, even though those are all the exact same element. So we would say that these 3 atoms are isotopes of each other. Isotopes are the same element. And we have multiple ways to kind of describe and designate these different isotopes. The first method is to essentially just say what the element is, hyphen, mass number. So, for example, uranium-235 or U-235. Right? So I could either write out the whole element name or I could just use the symbol. The number that comes after tells me what my mass is. So in this case, 235. Notice that, I can already say, I have 92 protons. Well, I would look at the periodic table, and I could go find uranium. I could go find U on the periodic table. If you have one handy, go ahead and do it. Look it up just to confirm that we're right. And you'll see that uranium is in the little box that has the atomic number 92 at the top. That number tells me how many protons I have. Because now I know my mass, and now I know my protons, I can do a little bit of subtraction to figure out how many neutrons that thing has. So by just telling a scientist U-235, you tell them the element, you tell them the mass, you tell them the number of protons, and you are able to tell them the number of neutrons. Typically speaking, this method 1 is how it would be used if you're talking about the element in a sentence. So you would say U-235 is what we have in this fuel cell, right? You're using that in a sentence. Our second method of describing isotopes is that really shortcutty kind of method that we opened with, where we just put the element symbol and then we put the mass number and atomic number on the top and the bottom. So I would have U-238. I would put my 238, my mass number, in the upper left, my atomic number at the bottom right, my bigger number is on top. And just from that, I would know that I have 92 protons, and I can pull my calculator out and do 238 minus 92, and that would tell me that I have 146 neutrons. Now, sometimes we're going to give you one where we don't even give you the atomic number. Maybe we just give you U-238, just like this. But here's the beauty of it. You can still figure out the number of protons. If you look at the periodic table, you'll find the box that says U. You'll look at the top and it'll say 92, in which case, oh, you know that there's 92 protons in there. You know the atomic number. You can still do all of the work. So do be aware that we don't necessarily always have to give you that bottom left-hand number. You can always go look it up for yourself. Even if you don't know what that element is, you can find the symbol on the periodic table that we give you. So we're going to do a few examples just to make sure that we're good at filling out and finding all this information. I promise you're going to have a table that looks just like this on your exam. Now, unless we specify otherwise, we're going to assume that we're working with neutral atoms. And I know we haven't really gotten to the concept of what does not neutral look like. We'll talk about that literally here in a couple of minutes. But for right now, we're going to assume that everything we're dealing with is neutral. There is no overall charge. So let's look at example 1. We don't know what that first element is. We have no idea. But we do know that I have a Z of 23, an atomic number of 23, and I know that I have 21 neutrons. Well, I know that my Z represents my number of protons. So just so that I can be super clear, I'm going to write P over my Z column and Z over my proton column so that I can remember that whatever number is in my Z column should be the exact same number in my protons column. Because remember, the atomic number Z is always the same as my number of protons. So if I have a Z of 23, I know that I have 23 protons. Well, my atomic number A, my mass number A, is whatever the mass of the atom I'm dealing with, whatever mass I have. Well, I have 23 protons, they have mass, and I have 21 neutrons, they have mass. So if I'm going to get my mass number, I'm going to do my protons plus my neutrons. And again, I'm going to put that over my A column just so I can remember exactly what number goes into that column. So 23 plus 21 is going to give me 44. And since right now I'm assuming that everything is even, if I have 23 positives, I'm going to need 23 negatives. Again, we're assuming it's neutral right now. We'll talk about when to not assume that here in just a little bit. So I now have everything except what the element is that I'm dealing with. So in order to figure that out, I'm going to have to go to the periodic table, and I'm going to look to see what symbol, what element has an atomic number of 23. So looking at the periodic table in front of me, you don't actually know the element that, or you don't have to memorize necessarily the element that has a V, but even if you don't know what the name of that element, that's okay. You should still be able to get this last column because you're just copying down the symbol. Well, the symbol of the box that's in atomic number 23 is V. And I know that my mass number goes on top, my atomic number goes on bottom, and I can get my symbol even if I don't know the element. But hopefully you've been practicing your elements. You know how to go name to symbol or symbol to name. Well, in this case, V is the element vanadium. And whenever I put the name of my element, I'm going to put the name, and then I'm going to put the mass number, vanadium 44. So you can get everything from just a little bit of information. So here's what we're going to do. I'm going to pause the video here. I want you to pause the video here, excuse me. And I want you to attempt these other 4 examples. Here in a little bit, the answers will just pop up on the screen. You can check your work. We're not going to run through every single one, but I am going to put the answers up or on the examples so that you can check your work. So pause the video here, attempt these 4, and the answers will pop up here in just a second. So here we have our answers, carbon-13 through sulfur. And hopefully they they should exactly match what you did. Notice walking through the carbon-13, we knew that we had carbon-13, we knew that we have 7 neutrons. From just the name of this atom, we can infer that it has a mass of 13. And because we know we have a mass of 13 and 7 neutrons, we could figure out that we have 6 protons, which would give us our atomic number of 6. Or, since you know it's carbon, you could just look at the periodic table and you could say, well, if I know that carbon is C, the C symbol is in the 6th block, so I know my atomic number is 6, which will give you your proton number of 6. Finally, you get over to the symbol, atomic number, or mass number over atomic number, 13 over 6, C. There's, generally speaking, multiple ways to go through these tables in order to get to the right combination of Z, A, protons, neutrons, and electrons. So keep practicing. If you're still struggling with coming up through these tables, I guarantee you will see one on the exam. So come see us. We will make example problem after example problem for you, and we can walk through it together. Now, before we move on, notice again, all of these atoms are considered neutral because we didn't tell you otherwise. We didn't specify that this is an atom with a charge. But what happens if something does have a charge? Well, if our atom does have a charge, we don't call it an atom, we call it an ion. So ions are charged atoms. Okay? And if it's charged, that means your overall number of protons does not equal your overall number of electrons. And that's a really important, distinct difference. Your number of pluses do not equal your number of minuses. Whichever one you have more of gives you an overall charge. So let's look at that first example. I have a symbol, 4020 Ca, with a +2 in that upper right-hand corner right there. That tells me that this atom has a total overall charge of +2. I have 2 more positives than negatives. So since I have 2 more positives than negatives, that's going to affect how many protons I have versus how many electrons I have. In those previous examples, we were allowed to assume that my protons equal my electrons, which means if my protons were 7, I would have 7 electrons too. That's no longer the case if I have an overall charge. Other than that, the rest of the table is filled out exactly the same. Our mass number is still this top number right there. Our atomic number is still that bottom number. So I know that I have an atomic number of 20, a mass number of 40. My atomic number is still my number of protons. That will always be true. So that's still 20 protons. Since my mass number is 40, my atomic number is 20. If I take the difference, well, 40 minus 20 gives me 20 neutrons. Ca, you could either look at the periodic table and look at, oh, well, box 20, I know that element. Or you could look at the symbol. My symbol is Ca. That tells me that I have calcium. And I add in my mass number, 40. The only part that is different, now that I have an overall charge, that potentially changes my number of electrons. I have 20 protons. I have 20 positives. But since I have an overall +2, I need to have 2 more positives than negatives. Well, since I have 20 positives, that tells me I should have 18 negatives, 18 electrons. I have 2 more positives than negatives, so I end up with an overall +2. Pause the video here. Try the next example on your own. In a few seconds, the answer will pop up and you can check your work. Okay, here are the answers for that second example. Notice again, everything worked out the same. 1632 from my symbol over there. 16 atomic number tells me I have 16 protons. Sulfur means 16 protons. 32 minus 16 gives me 16. The difference is this number of electrons. I have a negative overall charge, -2. That means I need 2 more negatives than positives. So therefore, 18 electrons. Which brings us to the end of the video. So work through your homework, work through these example problems. Like I've said before, you will see this table on a test, just like this. You're allowed to assume that it's a neutral atom unless we specify otherwise. If you ever have any questions, please ask, because we'd rather you ask than just take a guess and not get it right. So make sure you're doing those practice problems.